What happens when 41 stories of radically futuristic design reshapes one of the world's most recognizable and historic skylines?
I was described as public enemy number one.
How do you build a record-breaking bridge without foundations?
These are the kinds of problems that keep bridge engineers up at night.
And where do you begin with a gravity-defying cloud of glass and steel, described as architectural chaos?
We can build everything, and not in the stupid way of doing boxes. Yeah?
This is the age of the extraordinary.
It's like one of those insect-eating plants, only enormous and white.
Where ingenious engineers have unleashed unchecked creativity. Now their secrets are revealed. As we discover the inside stories of their construction.
This is an incredible feat of planning and engineering.
To try and understand, how did they build that?
For our first building, we're heading to England, where in 2001, one of the world's most celebrated architects set out to create an extraordinary building that would change the London skyline forever. With the address 30 St. Mary Axe, it clearly needed a snappy nickname, like the Rocket. Oh, no, the Cigar. Nope, Jay, I know what we'll call it. The Gherkin.
The City of London. Home to the Bank of England since 1694 and a financial powerhouse ever since. It's known for its traditional values and until 20-odd years ago, its traditional architecture.
It's really hard to imagine now, but apart from the Lloyd's building, that financial district of London was architecturally really quite dull.
Then, at the very end of the last century, the opportunity arose for a visionary architect to change all that. With a building that would drag the city kicking and screaming into a new millennium.
No one has ever seen a building this shape and size anywhere in the world.
41 stories of cutting-edge glass and steel that was ruffling feathers before it was even off the drawing board.
In the opinion page of a prominent newspaper, I was described as public enemy number one.
An extraordinary concept that forced engineers to use techniques never before tried in a building of this kind. This is 30 St. Mary Axe. Controversial, iconic, and one of a kind. It transformed the skyline of London forever and challenged engineers to redefine the possible. So, how did they build it? It's 1992, and a terrorist attack in the heart of the City of London provides an unlikely catalyst for change. A bomb is set off by the Provisional Irish Republican Army, killing 3 people and injuring 91 others. It damages the Baltic Exchange, a trading hall that has been at the heart of the city for nearly 100 years. The decision is taken to allow something much bigger in its place. Norman Foster, one of the world's most famous architects. Responsible for the Millau Viaduct in France and the Hearst Tower in New York, takes up the challenge of redefining London's skyline.
Can it give something back to the city of which it's part? In each of these buildings, they interact with the city. They try to give something back to the public, as well as creating something very, very special for the private spaces within the building.
What Lord Foster has planned for the site takes special to a whole new level. A 180-meter tall, 57-meter wide tower completely in the round. In order to reduce the impact at the ground, it will get wider as it goes up, before being topped with a dome of glass. An interlocking grid shell of 2-story high steel columns will interconnect at 18 different points every other floor. It will then be covered in an intricate skin made up of 7,492 panes of glass. In an incredibly high-tech world, here windows will simply open and close with the weather. The passive cooling system will circulate air through the building, cutting down on air conditioning and giving it some seriously green credentials.
The Gherkin was an object of derision. I think the name Gherkin originally was a hostile. In the opinion page of a prominent newspaper, I was described as public enemy #1.
Despite the press being against the building, in 2000, and with some trepidation, the planning committee grants permission to go ahead. A year later, the construction teams break ground.
Arriving here and seeing the enormity of the task was inspiring. You really felt like you were getting involved with something that was going to be out of this world.
The first challenge is to lay the foundations.
The base of the Gherkin is remarkably small, but because it swells as it rises, what you get is a very large building with a very small ground level impact.
It also creates a serious challenge, because it means the entire weight of the large building is concentrated onto the small footprint. Unable to spread the weight out, the engineers have to create some heavy-duty foundations to keep the building from sinking into the soft London clay.
You want to make sure your foundation's sound. People think that the building, that the bits they see of the building is complicated. There's an awful lot in the ground that's similarly complicated that you will never see.
The team starts by drilling piles. These underground columns, measuring about 5.5 miles in total, will hold the tower up. Each has to be engineered to within an inch of its life.
The load was designed for 117,000 tons. We drilled 333 piles into the ground. Collectively, that's 9 kilometres of straight shaft digging. The London clay gets harder the further you go down. And when I say hard, it's like steel when you get down the bottom. It is that hard.
With the piles drilled, the team plans to finish the foundations with a massive 8 feet deep concrete slab, connecting all 333 piles together. It's absolutely crucial that the entire slab cures at the same time. No mean feat when you're pouring this much concrete.
You could end up with the bottom of the pile cap curing before the top, and it's not bonded together. And that's not good.
The entire pour has to happen in one go. And the concrete is specially treated to make sure none of it cures till the last lot goes in.
There was an additive added to it which made sure that the first lot that got poured didn't harden until the top part had, so the whole lot could go off as one piece.
We had 3 concrete pumps, delivery pumps, situated on 3 of the corners, and we had 27 concrete trucks on turnaround bringing this concrete in from 3 different depots around London. So it was a military manoeuvre that took just over 12 hours of one continuous pour.
The crew pours over 63,000 cubic feet of concrete. But with meticulous planning, it goes without a hitch. Now, with a solid base to build from, the engineers get to work on the complex steel structure that will hold the building up. It's known as a diagrid.
The diagrid frame is a network of triangles, which are also hugely strong and efficient, but it also gives the building that unmistakable trademark skin.
The Gherkin and the Hearst Building in New York. And when you look at them, they both have triangulated structures. Why? Because a triangulated structure is inherently more rigid with less material.
Constructing it is the next challenge, because this is one of the first times a diagrid structure has been used to build a skyscraper.
Everybody here really felt this is the proper start of the project. Everybody around the city, anybody who was coming past, was going to view this building rising from the ground.
The plan is to start with the core of the building, which will act like the spine. The steel diagrid structure will be built around it and connected back to the core through a series of nodes in the steel frame, like the spokes on a bicycle, all watched carefully by the building's detractors.
The core itself was always 6 floors above building the outside structure.
There were 18 of these frames per floor going around before the next set come on top.
Then, as the building gets higher, something strange starts to happen that threatens the entire project.
Our engineering team started noticing things weren't exactly where they should have been.
Next, the teams have to find out what's going on. It's 2001, and in London, England, work is underway to build a revolutionary new skyscraper, but it's hit a major problem. For some unknown reason, the structure is moving. They have to find out why.
Our engineering team started noticing a constant pattern of errors. They did something in the afternoon. The following morning, when they checked it again, things were out of plumb.
After some serious detective work, the team discovers the culprit: London's famously changeable weather.
Steel changing its dimensions due to weather is a really big challenge in construction.
When steel gets hot, it expands, and cold, it contracts. And that is exactly what's happening here.
In summer in London, it can be freezing cold one day, and then the next day you have blistering heat. So the challenge becomes, how do you calculate for temperatures that you can't predict?
The only way we could correct it was getting the engineers to transfer working at night, when it was cold, and by and large, not very windy.
And by doing just that, they're able to get constant measurements and overcome the problem. But the challenges don't end there, because the engineers need to somehow counteract the building moving under its own weight.
You've got the 2,500 tons worth of steel, which gradually gets loaded. Each floor adds more weight. That weight obviously compresses down.
And it's a bit like overeating. Your stomach comes out, yeah? And it's exactly the same with this structure. As the weight come on, the circumference of the building grew. And each level was designed to settle by 40 millimetres. It did that to perfection.
The frame is designed with an extra bolt on each connection. So floor by floor, once the building finishes settling, the construction crews tighten them, creating a completely rigid structure.
The engineers who design these steel frames are getting so good at predicting deflection. They can keep tolerance to a minimum and so get narrower gaps in the framework and the facades, so you end up with a slicker finish.
The next challenge is getting that perfect finish using almost 80,000 square feet of glass. To pull it off, the team turns to what is at the time a revolutionary idea. They use cutting-edge computer technology for the design. The result is a pattern of 7,492 panes of glass, but they fit without a hitch. And somewhat strangely, in a building that's all about its curves, 7,491 of them are actually flat.
So the very last piece of glass to go in is the lens at the top of the building, which was 2.4 metres in diameter, 250 kilograms, and the actual capping piece of glass was lifted up by tower crane with the rope access guys going around it, installing the pressure plates that hold it down.
This building is different in so many ways from those that have come before it, and most that have been built since.
It's tighter at the base, it swells out in the middle, and it reaches a point in the sky which unusually is not devoted to mechanical equipment.
Most buildings have their air conditioning units on the roof.
The reason they sit outside on a roof is so that they get free ventilation to them. So bringing that inside the building was a challenge.
In order to pull this off, Lord Foster needs a system of cooling the building that does not completely rely on air conditioning. Its genius is in its simplicity.
There's 6 triangular light wells on every floor. There's 4 windows at the end of that light well. They're triangular windows, and they open up when the weather conditions are right.
If the building is getting too hot, the automated glass hatches open up. And if it's cold outside, the windows close to retain the heat.
The pine cone, which opens and closes according to the weather, it's pulling air through the lungs of the building. It's making it more healthy, fresher, and dramatically reducing the amount of energy, up to 50% less energy compared with a conventional building.
In December 2003, the Gherkin is finally complete. Stunning on the outside. And inside, thanks to reducing the need for air conditioning, there's a restaurant rather than a plant room at the top.
In that sense, it's almost unique because the top of the building is about the panorama of the city, the region. It's for the people, it's not for the machinery.
That continuous glazed domed roof with those 360 views, it is an exquisite design vision, only made possible by brilliant engineers.
My personal feelings when we actually completed was one of elation, pride. It was the best 4 years of my life. It's given an awful lot back to the City of London.
Anybody who was involved in this building has a huge amount of pride in it, and its legacy will withstand and will retain for many, many decades to come.
Born out of an atrocity and vilified before it was built, 30 St. Mary Axe has become a symbol of a new city of London. A building that is as clever as it is beautiful. A structure that challenged traditional thinking. And one that has changed the skyline for a very long time to come.
If I said I was going to build a road bridge across a lake 1.5 miles wide, but instead of securing the bridge to the riverbed and supporting it with huge towers, it would just float on the lake surface on 77 concrete pads, you probably think that was a crazy idea. The thing is, in Seattle, one thing they really love is crazy ideas.
And on the surface, that's exactly how it sounds. The problem was that Seattle desperately needed a new bridge to get people in and out of the city. But Lake Washington is so deep and the lake bed so soft that traditional bridge building is a no-no. So they've decided to construct the world's longest and widest floating bridge. It had to hold up a rigid road, yet somehow move with the natural forces of the water below. Building it pushed engineers into some seriously choppy waters.
These are the kinds of problems that keep bridge engineers up at night.
They had to create a mega dry dock from scratch, where they could construct the 77 enormous concrete floating pontoons.
Any imperfection could lead to the pontoon sinking to the bottom of Lake Washington.
Every piece had to be transported over 200 miles through the Pacific Ocean. This is the Evergreen Point Floating Bridge, a record breaker that took world-class engineering to realize. So, how did they build it? It's 1997, and in the Pacific Northwest, the city of Seattle is growing bigger by the day. A tech boom is attracting more and more people, making it one of the fastest growing cities in the U.S. But its infrastructure is starting to creak. And in particular, an old bridge over Lake Washington, a vital link to the city built in the 60s, which can't cope with the volume of traffic. There are regular backups for miles, and it's literally cracking under the weight. With the existing bridge at the end of its life, the designers find themselves in a race to replace it.
The weather, the traffic, the levels of the lake changing, these are the kinds of problems that keep bridge engineers awake at night.
Building this bridge over Lake Washington poses a unique set of challenges. Not only will it have to span over 1.4 miles, but solid ground is hundreds of feet below the surface. Don Oates is one of the design managers tasked with coming up with solutions.
Lake Washington's a unique lake. It's very deep. It's about 200 feet to the mud line. Because of the volcanic eruptions, it's actually filled with very, very soft soil to a depth of about 80 feet. And then below that, you'd have to excavate down about another 100 feet to be able to get to dirt that you could actually build a structural foundation on.
If you went with a traditional suspension bridge, like, say, the Golden Gate Bridge, you'll end up with towers that are about 400 feet tall before they even got out of the water.
Then add another 600 to support the suspension bridge roadway. That's a 1,000-foot tall tower. Not gonna happen.
The team takes inspiration from the old bridge and decides to create a new supersized floating bridge. This new bridge will have an extra 4 lanes and room to expand to take a light railway if it needs it in the future. The road will be elevated above the pontoons and cushioned with shock absorbers to stop vibrations from cracking the structure. And everything will be balanced on top of 77 floating concrete pontoons, anchored to the lakebed below. Now the engineers just need to float hundreds of thousands of tons of concrete.
Making something that floats out of concrete may seem quite unlikely, but actually it's just simple physics. Imagine this is concrete. Guess what? It sinks. But if I take the same amount of concrete and shape it into a cup, this time it floats.
Even though making the enormous concrete bridge float is possible, constructing the giant pontoons creates its own set of challenges. Firstly, they need a massive dry dock in order to build them.
A dry dock helps you build a boat, or in this case, our pontoon, in what is essentially a giant empty bathtub. When the pontoon is ready to float, the dry dock is flooded by lowering a massive gate, and the pontoon can float out.
We figured out it needed a basin about 900 feet long by 200 feet wide.
It's a huge area, roughly the size of 6 soccer fields, which is not exactly easy to come by in a busy, bustling city. In the end, the team finds a disused lumber yard 80 miles away in the coastal town of Aberdeen. Not exactly local, it proves to be one of the few places available to build the enormous dry dock. Overseeing construction of the pontoons and the brand new $367 million dry dock is Phil Wallace.
This is our 55-acre casting basin that we had down in Aberdeen, Washington. This basin was built so we could cast 6 pontoons, so 4 longitudinal pontoons and 2 of the auxiliaries in the back. We put in a gate in this area here to allow the pontoons to float out. We had over 600 employees working there at different times of days, working days and nights.
With the dry dock ready, work starts on building the pontoons, which will be cast using over 500 million pounds of concrete.
To make the pontoons, the engineers built a massive mold, known as formwork. Then they started pumping in concrete to fill it. This is a critical stage on any build.
Any imperfection could lead to a fault, then a fracture, and then ultimately to the pontoon sinking to the bottom of Lake Washington.
They're like 200 tons a piece. Everything's big. The most critical pour that goes in, it's the wall form pour. the exterior wall of the pontoon. And that pour, you need to make sure you have a good joint at the bottom.
Although the team strives to make each pontoon perfect, they're designed with the worst-case scenario in mind. Instead of being a single large space, they're divided into sealed compartments. So if one leaks, the others can still do their job.
So we're currently inside one of the longitudinal pontoon cells. You see hatches to the adjacent cells. All of these hatches are watertight, so keeps the cells separated in case there's any water entering any of these cells. So all of that is connected to the pontoon monitoring system, so there's alarms triggered in case any of these cells need to be pumped out.
It takes months, but eventually the pontoons are completed and moored at a nearby harbor. But before they can be transported to Seattle, the engineers need to create a system for anchoring them in place once they get them there. One that can cope with the varied lake bed and the forces of the water.
There were 3 different types of anchors for the different soil conditions that we had. The shaft anchor, 8-foot diameter steel shafts that go into the ground filled with concrete and a steel cage.
The next anchor type is nicknamed the Box of Rocks.
They're literally 40 by 40 by 20 foot tall. They look a lot like pontoons, but they're open top. They are 600 tons with all the rock in them.
The last are like a supersized traditional ship's anchor. 45 will be used on the bridge.
All the anchors we had to test for loads up to about 570 tons. So it's a massive load that these anchors can take.
The pontoons are cast. The anchors are set. It's now time to tow them the 260 nautical miles around the coast and into Lake Washington. But this means going out into the open sea. Here, the 360 by 75-foot pontoons will be at the mercy of the Pacific Ocean. In the Pacific Northwest, engineers are planning to transport massive cement pontoons through open ocean to construct the world's longest floating bridge in Seattle.
You got big tractor tugs that take them up the coast. We didn't float them until we knew we had a nice window where we weren't going to have any storm conditions. We generally could go 4 knots. That was probably the maximum speed those pontoons could take. So you're out there, a couple days in the ocean.
Moving each pontoon takes around 2 days. But finally, the 77 are in place. Now the engineers face their next challenge. Although the pontoons are anchored, they move with the water on the lake. Somehow they have to figure out how to fix this constantly moving bridge to the rest of the highway, which is fixed on land.
Fixing a stationary structure to a moving one is incredibly difficult. In this case, that structure is floating on a lake. All kinds of things can happen to make that structure move.
The transition span was one of the more complicated pieces of infrastructure we had to build. The floating infrastructure moves, fixed structure hopefully does not, and so you have to figure out how to connect that.
They turn to automotive engineering for a solution.
We put it on what we called a large trailer hitch.
Just like a tow hitch, this has spherical bearings that let the floating section of the bridge move up and down and side to side. It's these that keep the bridge from tearing itself apart.
With each pontoon connected by massive bolts and cables, a raised roadway is added to the top of the pontoons. To prevent it from cracking, the entire 6-lane wide road sits on special shock absorbers.
So we're currently standing on one of the longer longitudinal pontoon. This is 360 feet, so about a length of a football field. This makes a majority of the foundation that's holding up the bridge structure above us. You can see on all the columns here, there is bearings sitting on them, so it allows for a little bit of movement there in the roadway. Those are pretty much cushions that the roadway is sitting on. So along the entire bridge, you can see there's hundreds of these holding up the bridge deck on top of all the columns.
Finally, after 4 years, this 1.4-mile-long record-breaking floating bridge is in place. And the first people who get to use it are the families of the dedicated men and women who helped build it.
We actually had a family day where all the workers that had worked on the job were invited out to walk the bridge. So the people that built the bridge actually got to see it first. And then a couple days later, the state had a big celebration, and over 50,000 people showed up for that celebration.
I mean, there were some hard times, and we went through some really stressful events and some ones that you kind of laugh at now when you kind of think back at them. But there's a lot of pride that we have from it.
This simple ribbon of road hides its importance as a marvel of innovation and engineering. While for locals, it's a lifesaver, giving them back all those hours that would have otherwise been spent sitting in a traffic jam.
As in all fields of creativity, it's easy to think that surely by now, everything possible in architecture has been done. I mean, there can't be any more genuinely original ideas, right? But back in 2001, a call went out to design a new museum of science and anthropology for the French city of Lyon. The opinion-splitting building which resulted was totally unlike anything that had gone before, nor has there been anything else like it ever since. Mold-breaking design classic or just architectural chaos? You decide.
Take one tiny spit of reclaimed land, sitting where two rivers join.
We said we should move it. The government said, no, no way.
A French city that wanted to create a building for which it would be remembered.
A building that's a cloud with a whirlpool in its ceiling, only in France.
And an architect with a passion for the extraordinary and a hatred of the ordinary.
I hate columns.
And what they got was a building so complex that even its designers couldn't predict the final result. And where, from the metallic cloud-like front to its crystalline back, every piece seemed more complicated than the last.
Even for us architects, is how will it really look like?
Nicknamed the Cloud, this is the Musée des Confluences, a gravity-defying mercurial structure, which would push both architects and engineers to realize the impossible. So, how did they build it? In 2001, the rather traditional city of Lyon decides that it's going to bring new life to a small, neglected part of the city. A thin spit of land that was created over 100 years ago and sits where the Saône and Rhône rivers meet. Until now, it's been little more than a local picnic spot. But the city has bigger plans. They want a centerpiece to attract new investment to the city on both sides of the river, and decide on a new museum building to symbolize the coming together of the two rivers with a meeting of minds. Now all they need is a design. They turn to award-winning architect Wolf Prix, whose buildings are as extraordinary as they are beautiful. The Musée des Confluences is going to be no exception.
We can build everything, and not in the stupid way of doing boxes. We try to liberate space. It is not a museum. It's a cloud where knowledge is traded.
The city only puts one constraint on the design. It mustn't block public access to the end of the point. The land is so narrow, this could seriously restrict what they can build. But Wolf has an idea.
The concept of the building was not only to organize the exhibition spaces, but to lift up the building so that people can walk to the point of confluence and the park here.
The final design is a gravity-defying building that lays down the gauntlet to the engineers.
how can we build it, because it was like a flying building. You have no idea how you can work with the architect just to understand what is willing, what is the objective of the architect.
It's clearly going to be an enormous challenge for the team. First, they will need to build a solid base that's strong enough to support the weight of the building, while holding up the huge columns that will make it appear to float. Next, they will have to construct a steel frame which will rest on top and be covered in 64,000 square feet of stainless steel sheets to create Wolf's Cloud. Finally, they will build the Crystal, a spectacular entrance made from flowing glass panels set into a thin steel frame. At its heart will be a whirlpool, 108 feet high and built of specially curved glass. It's known as the Gravity Well. In 2010, construction begins, and immediately the team faces a major challenge. They may have plans for an extraordinary modern building, but they're expected to build it on land that literally sucks.
Building on reclaimed land can potentially run into all kinds of issues. That area may be more prone to flooding, and because that land may have once been a river, it might be more unstable and prone to subsidence.
Next, even the architect has second thoughts. In 2010, in Lyon, France, work is underway to build a magnificent new museum. The only problem is, it's on reclaimed land, made up of loose sand.
We said we should move it. The government said, no, no way. This is the most important point in this city.
So engineers designed foundations, which include 570 deep piles, with a reinforced concrete slab sitting on top. Onto that, they plan to fix the columns to hold up the massive cloud.
We had to put a lot of piles in to reinforce the earth. We also lifted up even the plinth, the concrete part of this building, to be over the groundwater.
It takes time and an awful lot of concrete, but there are now solid foundations. The next big challenge is to work out how on earth they're going to build the enormous show-stopping cloud. To make it appear to float, they take inspiration from an old-world engineering idea.
Construction of the cloud is the construction of a bridge.
A girder bridge is perhaps the most classic bridge design that you and I are most familiar with. The bridge deck is held up by huge iron or concrete girders that transfer the load to the supporting columns.
At its heart, the complex floating structure is made up of a series of interconnecting steel beams. These allow the team to create the unique cloud-like shape. And just like a bridge, the forces from this are transferred to the ground through a series of columns. But its extraordinary irregular shape makes it difficult to calculate how the loads will work. A miscalculation could lead to the engineering failing and the building collapsing.
The cloud is very hard to understand and to describe because it's a cloud. So how do you describe the shape of the cloud is not possible.
Hoping to make the impossible possible, the team tries to build a computer model, but even that's not easy.
You let the computer working one day, you come back after one day, you look at it, it doesn't function. You have to try another solution. But you wait always one day to have the response of your idea.
Eventually, after some serious number crunching, the engineers arrive at a structure that is as stable as it is breathtaking. The construction crew gets to work building it.
Here you have really complex connections of these different secondary steel structures. It worked well due to this really sophisticated 3D model.
Once the main steel frame is in place, The team then creates its irregular shape by constructing a smaller frame on top, which is clad in 64,000 square feet of stainless steel paneling. The next challenge facing the team is how they're going to build the crystal, a massive glass atrium which will go at the front. A challenge Wolf isn't making any easier.
Basically, I hate columns. To dissolve a stupid column in many parts was the goal.
Wolf wants to have an open space, but it's vast, and they need to find a way to support the roof.
Because of this interaction between all the elements, it was very hard to achieve the structural design of the crystal.
The solution for how to support the roof lies in an extraordinary idea.
Imagination comes from the turbulences when two rivers coming together. This is the experiments we did in our office to see how a turbulence looked like when two streams coming together. Then this is the plan. It's a column without being a column.
Wolf's idea is to create a support that doesn't look like a column. So they make a void in the middle of the atrium, almost as if a giant finger has pushed the roof down to touch the floor. Constructed from glass and steel, it looks perfectly in place with the rest of the structure, but it's also supporting the entire roof. The extraordinary mix of sculpture and engineering is nicknamed the gravity well.
If your structure contains a cone-like shape that's tapered to the ground, the forces will be transferred to the apex or tip of that cone. So this shape is not only interesting architecturally, it also serves a structural purpose.
The next challenge is making the structure strong enough to be able to deal with 15 feet of snow. They start with the cladding of specially reinforced glass panels. But the clever engineering doesn't stop there.
We have in the lower parts, we have heated glass panels. The drainage is also heated, and the structure is strong enough to take the pressure of snow.
Finally, in 2014, after 4 years of construction, the Musée des Confluents is complete, and the results are extraordinary.
It's a very open, special, not museum. It's a building for trading knowledge.
I'm very, very, very proud, and it was really great to be part of this team.
Maybe one time in your life you make this kind of project, so all your life you will remember, and you will remember this experience.
This cutting-edge design transforms what a museum can be. Creating an open, welcoming space that beckons people in. And just like the two rivers that surround it, it will bring people together for years to come.